Questions about anything from last time? So last time I was motivating the definition of the Fourier transform, or the Fourier integral, the real version. And the motivation was to write out, let's say I had a function that had compact support. So it's 0 outside a big interval. And let's say it's as nice as you want. I took it to be twice continuously differentiable and to be 0 outside of some interval. Then the idea was to expand it in a Fourier series and let the interval go to infinity, get bigger and bigger, and see what you get. And when you look at it and take limits in the right order and put it all together, you realize that you can expand f as an integral. And if you think of that as a Riemann sum in the w variable, then you realize I'm expanding f in terms of all frequencies, cosine wx and sine wx, where w are, if on a Riemann sum, they would be going along the real axis from 0 out to infinity. And so that's like a really dense Fourier series with all the frequencies involved. Remember when we had 2 pi periodic things, we only needed the frequencies that were 2 pi periodic, and those were the musical frequencies. But when something's not 2 pi periodic, well, then you would expect to need more frequencies, and maybe even all frequencies. Okay, and those functions a, w, and bw are given by formulas. And those are integrals from minus infinity to plus infinity, so the whole interval. Whereas the integral above is only from 0 to infinity in the w variable to have positive frequencies. Okay, so of course I was kind of wishy-washy in the way I deduced this thing, and I took some liberties without explaining it or proving it. We'll do proofs, or at least get into more depth about why it all works later. Let's see, I want to mention a fact. Were there any questions about anything? Well, homework 6 is due tomorrow night in grade scope. Okay, so that was the summary, and the fact is when does this work? Well, if f is piecewise C1 smooth, and let's see, that then such a function would have Riemann integrals, and if it goes to 0 fast enough at infinity, you would hope that it'd be absolutely integrable. So the integral from minus infinity of the absolute x f dx is finite. So that's called being absolutely integrable. So I'm letting my piecewise C1 smooth function have jumps, like I did with Fourier series. Then the fact is, then f of x is equal to its Fourier integral. And I'm going to put equal in quotes here, like I did back with Fourier series. So it's equal to its Fourier integral. In the sense that let's see, it's equal to f of x where it's continuous, where f is continuous, no jumps. But it's equal to the midpoint of jumps at jumps, kind of like Fourier series. at jumps. Okay, that can be proved using basic analysis. It's kind of awkward proof without using the fancy things I'm going to do later. I'm going to use Schwarz's theorem, Schwarz's tempered distributions. They're very special functions that are nice and smooth and go to 0 and infinity incredibly rapidly. And if you dwell on those, you get the basic facts about Fourier integral quite easily. And you'll notice that Stein quotes. By the way, you should start reading the chapter 5 on Fourier transform. Stein opens that chapter with a quote of Laurent Schwarz and his theory of distributions, tempered distributions. So let's see. Let's talk about an example here that demonstrates this theorem. Let's take an easy function to begin with. Let's take a function that's 0 to the left of minus 1 and 0 to the right of plus 1, and it's just 1. Put that in the middle better. There. Okay, I want it to be 1 from minus 1 to plus 1. And then 0 out here. So there's two jumps there. And this is the f of x. So I'm not going to give it a value at the jumps. You could give it any value you want. And we're going to see that the Fourier integral is going to go to the midpoint of those jumps. That's the f of x. Notice that it's even. That's going to be an interesting thing. So now when I compute some of those things, like the a of w, let's see, I'd get a 1 over pi integral from minus pi to minus infinity to infinity of my f of x, or f of t, cosine wt dt. Well, I'm assuming that my function here is even. Cosine wt is an even function in the t variable. And so those two, when you multiply two even functions, you get an even function. And so I'm integrating from minus infinity to infinity, which is a symmetric interval about 0. And so this integral is just 2 over w times the integral from 0 to infinity of f of t cosine wt. And f is 0 to the right of 1 and 1 between 0 and 1. So that would be 2 over pi integral from just 0 to 1. That's where f is 1. So 1 times cosine wt dt. And the rest of the integral would be 0 from 1 to infinity. So maybe I should put plus 0 for the rest of it. And that's an easy thing to calculate. That would be 2 over pi. Let's see. Antiderivative of cosine wt. W acts like a constant in that integral. And that's 1 over w sine wt. Evaluated in between 0 and 1. Well, sine of 0 is 0, so that's just the a of w is 2 over pi times w. Let's write it like this. 2 over pi. When I stick in time t equal 1, I'd get sine of w. Sine of w over w. Well, that looks like it has a nasty singularity origin where that would be sine of 0 over 0, but that's a famous limit. That function's perfectly fine as you let w go to 0. That famous limit is 1 as w goes to 0. So that's not a bad function at all. And to save ourselves some work with the other function, let's note that, let's see, this is going to be 1 over pi integral from minus infinity to infinity of my f of t times sine wt. This time, we're going to get a major simplification by noticing that f is even, sine of wt is odd in the t variable, and even times odd is odd. And we're integrating over a symmetric interval. And so that's a big fat 0. Symmetric interval about the origin, that's a big fat 0. By the way, that integral from minus infinity, thing to note here, note, integral from minus infinity to infinity is equal to the limit as a goes to infinity of the integral from minus to a. And those integrals would all be 0. And so the limit of 0 is 0. That's an important thing to note. And I can do that because f is absolutely integrable. If it weren't absolutely integrable, then of course there would be some delicate things to think about, because it might happen that the integral from a to infinity is 0 for some a and not 0 for others. Things get weird like that. So the reason I can do that is because f is what's called absolutely integrable. Okay, so now I've got my a and my b, and so now I would write that f of x is integral from 0 to infinity. My a function was 2 over pi. Was it 2 over pi? It was 1 over... What was my a function? Where did 2... Oh, the 2 came from the symmetry. Yeah, it was 2 over pi sine w over w times cosine w. Let's see. Cosine wx. And now we're integrating dw. That's a weird thing to look at. That's an expansion of f in terms of cosine, wiggling cosine things of all frequencies. Hard to imagine why you'd want such a thing, but fascinating. That fact I told you about tells me that integral, even though it looks pretty hairy and probably beyond my ability to compute, I couldn't find an explicit antiderivative of that thing. But nonetheless, you can show that that would converge to 0 when x is less than minus 1. Let's see, the midpoint of the jump is a half when x is equal to minus 1. And then it would be equal to 1 when x is between minus 1 and plus 1. And then the midpoint of the jump is at x equal 1 is a half. And then after that, it's going to be 0 again. So that would be for x bigger than 1. That's pretty wild. let's think about the x equals 0 case. Let's let x equals 0 in that integral above there. Let's see, if x is equal to 0, then cosine of wx, I'll put this in a box. That's a Fourier integral. When x is equal to 0, cosine wx would be always 1. And so what happens when I would get that, let's see, f of 0 is 1. And that would be equal to, what the heck is it equal to? Sorry. 2 over pi integral from 0 to infinity of sine w over w times 1 dw. And so we get this famous fact that you demonstrated using the Dirichlet kernel. So we get the fact that the integral from 0 to infinity of this famous function sine w over w dw is pi over 2. And because, let's see, that's an odd function divided by an odd function, that's an even function. And it doesn't blow up at the origin. And so that means that the integral from minus infinity to infinity of this famous function is pi. You demonstrated that in the homework using the Dirichlet kernel in a clever way. In fact, in the Riemann-Lebesgue lemma. Questions about that? So you get some famous integrals out of this fact about the Fourier transform at some point. That brings me to sort of the main topic of today. I'm saving demonstrating some of these facts for later. Right now I want to show you what they're good for. And so I'm going to talk about the Fourier cosine and sine transforms. These are useful. And they get used by engineers to solve things like heat problems. We did a heat problem on an interval using Fourier series. If you have a heat problem on a semi-infinite thing, then you might use these transforms, and I'll show you how you do that. So the step one is to consider what happens when you have an even or an odd function. What happens to the Fourier integral? When f is even or odd. Let's do the even case first. F of x is even. Well, then let's see which one of those integrals is going to be 0. Well, we did it just a minute ago. Remember, I got a of w. That was 1 over pi integral from minus infinity to infinity of f of t cosine wt, cosine w times t dt. And this is even. This is even. And so the product was even. And I got 2 times this integral. That's interesting. I got 2 times the integral from 0 to infinity. So that kind of simplifies a little bit. And the B one turned out to be 0. We would get 1 over pi integral from minus infinity to infinity of an even times the sine thing would be odd. And that's even times odd is odd. And that would be a big fat 0. Well, that's kind of a weird thing to look at, because that looks incredibly like my Fourier integral. So if you stare at this for a second, I see that f of x is going to be equal to its Fourier integral, which is the integral from 0 to infinity of a of w cosine wx d of x. Okay, so that looks like an integral with cosine, but my a of w above there, where a of w looks like the same stupid thing, except there's a 2 over pi in front. So 2 over pi, same kind of integral from 0 to infinity, but here we would have f of t cosine wt dt. Incredibly similar. It kind of feels like if I take f, I multiply it by something that wiggles like crazy, and integrate. I get something. That something is a of w. Then I do it again. It looks like I'm doing the same thing again, and I get f back. That's mind-blowing that that's conceivable. The only thing that's different is that stupid constant 2 over pi in the two things. And so here's a brilliant idea. This is the Fourier cosine transform. It's the Fourier cosine transform is, I'll call it f sub c for cosine, transform of f. Okay, I want to do it twice and get back to this, my starting function. So I'll put a square root of the 2 over pi. So when I do that twice, it would multiply twice, and I'd get the a of w in there properly. So let's see. And that's going to be an integral from 0 to infinity of the function f of t with cosine wt dt. Let's see. Yeah. Let me make this an x. It doesn't matter what you call it. I want to make this a dx. But the fascinating thing is you do it twice. You get f to an a and then a back to an f. So the fantastic thing, let's see, what does it do? It takes Fourier cosine transform, takes a function on 0 infinity and maps it to a function on 0 infinity. Okay, so we got it. If I take a function on 0 infinity, I would extend it as an even function, and then study the Fourier integral, and realize that what I get when I do that thing twice so the fantastic thing is if I do it twice, I'm sending the function back to itself. That is freaky. I'll put that in a box. Okay, to understand the Fourier cosine transform, I start with a function on 0 infinity. I'd extend it as an even function, and then I do the Fourier integral. And then I would restrict to 0 infinity to see that my function got preserved. So I should maybe put in parentheses to understand we needed to extend f to the whole real line as an even function. And use the Fourier integral. Fact. Of course, we're assuming f is nice enough that we can apply that theorem. And we wouldn't care about the jumps, or what the thing was defined at the jumps. Maybe we'd avoid jumps altogether and use the Fourier integral. Okay. Well, you can do the same thing with the sine function. I won't write it out in gory detail, but similarly, so repeat the whole business, repeat the ideas for f of x, an odd function. And you get the Fourier sine transform. Which is Fourier thingy sub s of f. We're going to have the same square root of 2 over pi, so that when I do it twice, I would get a 2 over pi in front. And that would be an integral from 0 infinity of f of x sine wx dx. And then the big fact, it maps functions from 0 infinity to functions to 0 infinity. And the big fact is that if you do it twice, the Fourier sine series, I'll write it like this time, of the Fourier sine series of a function is the function back. It doesn't matter what you call the variable. That's a dummy variable. So you can call it w, you can call it t, you can call it x. Okay, well, some other key properties that make it very much like the Laplace transform. So here's some other key properties that make these things really useful. Let's see. I'll list them like this. The Fourier cosine transform of f prime turns out to be, well, that's a function of w, and it turns out to be multiplying by w, just like the Laplace transform did. And just like the Laplace transform, there's an annoying little thing which actually is a good thing, involving when you do integration by parts, you get a boundary term at 0. And let's see, to deduce this, to make sure I understand this part, I need f of x to go to 0 at infinity. As x goes to infinity. To get that term there and understand it properly. Okay, well that's a reasonable thing for a physical problem, like if you're studying heat. Unless the universe has an infinite amount of energy, you would expect things like that, heat, to go to 0 at infinity. So things like that are going to be expected when we use this thing. And there's a similar one for the Fourier sine integral transform. Namely that the Fourier sine transform of f prime is minus w. That's kind of annoying. It's different than the Laplace transform. Whoops, I botched that up. The Fourier cosine transform of f prime is w times the Fourier sine transform. So maybe I to emphasize that that's weird. I'll make that red. And this one is the Fourier cosine. So it jumbles up these things of f. And what's interesting, there's no weird term coming after this one. No minus anything. So that's different. Okay, so those are the big the facts about transforming derivatives. Do it again. Do these again. After all, many of the operators of physics and engineering are second-order operators. And so naturally, you might have to do this again. And when you do it, let's see, you get the Fourier cosine transform. Should I do it? Why not? Let's see, I'll summarize what I get when I do it. When I do them again, then it would jump, it jumbles cosine to sine. Then I do it again, it would jumble the sine back to the cosine. And so this turns out to be minus w squared. I go back to the cosine. And then I get a minus square root of 2 over pi f prime of 0 here. And when I do it to the sine one, it would jumble it back again to the sine transform. And that's also a minus w squared this time. And this would be plus the square root of 2 over pi. F of 0 times w. So those four things are interesting. I guess I should show at least why one of these things is true. They're not hard. It's just integration by parts. So let's do the easy. So here's a y. An example y. Let's see, if I were going to do the cosine transform of f prime, let's see, that is by definition square root of 2 over pi, integral from 0 to infinity, f prime of x, cosine wx, dx. Okay, and so this is a limit as a goes to infinity of the square root of 2 over pi, integral from 0 to a. And now I'm gonna trade these places. Cosine wx, that's going to be my u, and f prime of x dx is going to be my dv. And so let's see, du would be minus, that's where the w is going to come from. It'd be minus w sine wx dx. And v is just an antiderivative of f prime. That would be f of x. And so integration by parts, that's going to be the limit as a goes to infinity of square root of 2 over pi. Let's see, I'd get u times v. That would be f prime of x. I'm sorry, v is u times v. U is cosine wx. V is f of x. And that would be evaluated between 0 and a. And then I'd have minus a minus here. That'd be minus the integral from 0 to a of v du. And du, that's a minus the w, so that's where the w comes from. I can pull that out front. And sure enough, I'm going to get a sine transform here. Get that 5 out of there. Can't. Okay, so, and this is where the fact where I will need to know that f of x goes to 0 at infinity. That would make that term right there. This is going to be square root of 2 over pi. When I put in 0, I would get minus, cosine of 0 is 1, so it would be minus 1 times f of 0. And the cosine a thing is going to wiggle like crazy, but I want the f of a is going to go to 0. So that's going to be minus 0, because the cosine wiggles, that's annoying, but at least the f of x goes to 0, and that's because I need that f of x goes to 0. Oh, you're right. This would be a plus. Plus, right. That's where I'm letting the a go to. I should have put the 0 in front, because f of x goes to 0 as, or I should call it a goes to 0. F of a goes to 0 as a goes to infinity. And then I get minus a minus, and that would be a plus. I'll put the square root of 2 over pi here. And the w comes out in front, and what I'm left with is an integral from 0 to infinity of f of x sine wx, and that's the Fourier cosine transform. So sure enough, check. Spits it out. And they all go exactly like that. And you have to, so we're going to need not only to get those second derivative ones, we'll need the f primes to go to 0 at infinity also, which is reasonable to expect if it's a physical thing like heat. Let's see. And the one for sine is easier. The f of s of f prime is even easier. I guess it's not even easier. It's slightly more straightforward. There's no stupid term hanging out there because sine of 0 is 0. So there's not that annoying term to deal with. Okay, so here's a heat problem. So I'll do an example next time. So here's a big application. A heat problem on a semi-infinite hot wire. Okay, so let me have a hot wire here, starting at 0. So here's the hot wire. This is the x direction. And I'm going to measure the temperature. So this is going to be the U of xt is going to be the temperature. Temperature at x at time t. And I'll take my temperature to be 0 at 0. I'm going to refrigerate it there. And so my temperature is going to be 0 there, and I will make it go to 0 at infinity. That's going to be my f of x. The heat equation is du dt equals c squared d2u dx squared. And the initial condition let's see. My initial thing is my initial temperature. My initial condition, U at time 0 is that given temperature distribution. And I don't want to have an infinite amount of energy, so that's why my thing is going to go to 0 and infinity. Otherwise, I'd need a infinite amount of heat to heat that thing up. Let's see. And so that's the initial condition. And the boundary condition, I'm keeping it refrigerated at the left endpoint. So U is being held at 0. That's a homogeneous boundary condition. So it's like slapping on a refrigerator on Well, you ask yourself which of the two transforms would be useful. And because f of 0 is 0, let's see, if you go back and look at my two transform formulas, where are they? This one right here, notice there's an f of 0 out there. That f of 0 would be 0 when I take a transform of it. So, and I would just get that the Fourier sine transform is minus w squared times the Fourier sine transform of f in the f double prime. And this one has an f prime. Minus f prime is 0. That would be relevant if I insulated the left-hand side, because then there would be no heat flow. So that derivative would be 0. F prime of 0 would be 0 if there's no heat flow. So that would be the one I would pick if I had an insulated end. Okay, so the inspiration now is you stare at those a while and think, how could I use them? The big idea apply the Fourier sine transform in the space variable, not time. X, that's the x variable. Okay, what would that do for me? I'm probably going to do the work next time. Let's write. This is the typical thing to do in the subject. I want to take a transform. I'm going to call the transform function hat, u hat. So u hat, it's going to be a function in the w variable now, in the space variable, but t is just going to float along. So that's going to be the Fourier sine transform. So square root of 2 pi, integral from 0 to infinity of u of xt, t is floating along, sine x, wx dx. Okay, the t floats along and I get a new function of w. Okay, so let's think about the PDE here. This will get me ready to start next time and finish this off. So the question is, what happens to the PDE? Okay, I've got my let's see, what I'm going to take my I take the derivative of that thing above there. So when I take it, I would take du hat dt. And since these things are going to 0 to infinity nice and fast, we could hope that we could differentiate underneath the integral sign. So we're hoping we could take d by dt under the integral sign here. And this is supposed to satisfy the heat equation. So du dt, I'm going to take the c, well, that would be a c squared d2u dx squared. So I'd be taking the Fourier sine transform of the second derivative. And so this is the Fourier sine transform of the second derivative, d2u dx squared. This is where I'm going to say, let's take the c to be 1. So I don't have to think about that. Okay, so that's the Fourier transform of a second derivative, and that is just going to spit me out minus w squared times the Fourier sine transform of u, letting the t float along, minus, minus the square root of 2 pi f of 0 as u of 0. And that's 0 because we're keeping the boundary condition. That's equal to 0 by the boundary condition. So the aha moment here is I get my PDE is going to turn into an ODE. I get du hat dt equals minus w squared u hat. That feels like an ODE. So I turn my PDE into an ODE.